And using the discriminant formula helps us to determine multiple things about what your answers will be. If D, the result, is greater than 0, then you will have two unequal roots. If D equals 0, you will have a double root. In other words, the same answer repeated twice. And if your result in the discriminant is less than 0, making it a negative number, you're going to have two imaginary conjugates as roots. Okay? So greater than 0 will result in two unequal roots. Less than 0, two imaginary conjugate roots, so the I will be thrown in there. If they're equal 0, it's just going to be a nice little double root. Okay? So in the oral exercises, they had us solving a couple of these. And they want us to give you the discriminant. So b squared minus 4 times a times c is 36 minus 12. Did y'all come up with 24? Based on that, you will have two unequal, if I were asking you what that means, you'll have two unequal roots. Okay? Two unequal roots. Number 3, another one that's pretty easy, x squared plus 8x plus 16. So b squared minus 4ac, so 64 minus 64. Did y'all come up with 0? Going to have a double root. Double root. Number 5. T squared. Again, we're just practicing with easy ones here. 5t minus 5. I'm sure the one that Ginny's wondering about might be something like number 7. Yeah. So b squared minus 4ac, 25, negative 4, positive. So you should have come up with a 45. This one was a double root. This again is going to be two unequal roots. When I solve this, I better have two unequal roots based on what my discriminant's telling me. 7. 5x squared plus radical 5x minus 1. What you might not recognize here, and because of the way I wrote it, it's probably clearer. This is A, this is B, and that's C. So b squared, which is radical 5 squared, minus 4ac. So 5 minus, well, no, it's going to be plus 20. Negative, negative. Okay? So when you see that x that's kind of attached, it's outside. Radical 5 is the coefficient. 9 is the same thing, only uglier. Nine says, so this one would be two unequal roots. So last one, number 9, radical 5x squared minus 6x plus radical 5. All right, a squared, or b squared, minus 4ac. That's convenient. So 36 minus this times that, the square root of 5 times the square root of 5 is 5. So that becomes 4 times 5. 36 minus 20, 16, 2 unequal roots. All of these numbers were greater than 0. We didn't find any 2 imaginary conjugate roots in this exercise. When you guys did the odds yesterday, were there any that you wanted help with before I go on to example 3? Yes. Okay, go ahead. What do you got? 9. 9 and 11. 9 and 11. Okay. Pull out my workbook to make sure I don't make up any mistakes. And give it a whirl. Oh, yeah. So 9 is d squared plus 7/3 d equals 2. When you have these problems and the coefficient is not an integer, in other words, the coefficient is a fraction or a decimal, your simplest bet is to multiply the entire thing by 3. And in doing, or by the denominator, or if there's multiple denominators, the lowest common denominator. So by doing this, 3 times d squared is 3d squared. 3 times 7/3 d, 7d, and you end up with your 6. Okay? Zero it out. And you now have an equation ripe for discriminating. All right. So number 9, b squared minus 4ac, 49 minus negative 12 times negative 6, so 72. If I did my arithmetic right. Plus, yep, that should be a plus. Thank you. Thank you. 121. So this is going to be that kind of scenario. Okay, 2 unequal roots because we have a number greater than 0. So this fractional business, to get rid of those fractions, you're going to want to do something like that. You had 11 also. Does that make sense, getting rid of the denominator, clearing fractions? It's probably been a while since you've even seen that, because we don't have to do it that often anymore. Number 11, 2u squared minus 5u plus radical 8. So this one's already zeroed out. There are no fractions. So we are going to go with the flow here and see what we end up with. We're going to simplify this real quick, though. Makes it a little easier to work with. Okay? By simplifying that, that's going to help us out a little bit. I mean, we could have left it like this, but it's just easier to work with like this. All right. B squared, negative 5 squared minus 4 times 2 times 2 square root of 2. Okay, so positive 25. This is going to stay negative because these numbers are positive. 4 times 2 times 2, 16 radical 2. And if you actually simplified this, you're going to end up with 13.69, and that's a good approximation. In any case, let's just assume you even threw this out, which you wouldn't, but let's assume you did. 25 minus 16 is 9, or 25 minus 10 is 15, is 9. So 9 is still greater than 0. So you're going to have 2 real unequal roots. Okay? Again, all they're looking for is the nature. They're not actually looking for the actual numeric result. So if you find something greater than 0, you have an answer. which leads me to example 3. If I give you an equation, for example, k, x squared plus 12x plus 9k equals 0, has different roots for different values of k. So depending upon what I have here or here, I might end up with different roots. Okay? So the question is, what must I have to have a real double root? Okay? Using this, what must k be in order to have a real double root? Well, a real double root has a discriminant of 0. Would you agree? A real double root has a discriminant of 0, which means b squared minus 4ac has to equal 0 in order for me to have a real double root. Okay? Let's do that with what we have. A, b, and yes, ugly duckling, 9k is c, because the c value is a number created by whatever 9 times k is. Okay? So b squared, 12 squared negative 4 times k times 9k. Okay? b squared minus 4 times a times c. So 144, and all of that has to equal 0 in order to have a real double root. 144 minus 36k squared has to have equal 0 in order to have a real double root. If I subtract 144, divide by 36, negative, I end up with k squared equaling 4. So the k value must either be a positive or a negative 2. Okay? It has to be either a positive or a negative 2. If you plug in a positive 2, boom, boom, you will come up with a 0. If you plug in a negative 2 here and here, you will end up with a solution that is a real double root. Okay? The second scenario, and keep in mind that this b squared minus 4ac is going to be used over and over again, because to find a real unequal roots, my discriminant has to be greater than 0, doesn't it? According to the rules. So that means 144 minus 36k squared's result needs to be greater than 0 in order to obtain real unequal roots. Okay? Now this is where it gets a little weird. Solving it looks the same. Negative 144, divide by 36, divide by negative 36, k squared is less than 4. K squared is less than 4. So k is less than negative 2 or positive 2. That's a little sketchy. Okay? You can't think of it this way. Now I know you're thinking, why not? It equals it over here. Why doesn't it work over here? Well, look when they give you a little bit of an explanation there. It can't be both and still satisfy. So what you're saying, if you say it this way, it's less than negative 2 and it's less than 2, that would mean anything smaller than 2 would work. That's what that means. That being the case can't be so, because let's assume I use a 1. How about a 1? Well, a 1 is not less than negative 2. So you cannot answer that question that way. Okay? The proper way to answer this is to say the negative 2 is less than k, which is less than 2. Because what you're actually dealing with is the absolute value. Okay? the absolute value. So it's not going to be a positive or negative. When you're dealing with less thans and greater thans, as you're going to see in the next scenario, you're dealing with absolute value. Less thans or greater thans, use absolute value and apply it. Okay? How about real, or let's do imaginary. Imaginary roots, the discriminant has to be less than 0. And we're going to end up all in the same spot. We're going to subtract over our 144. We're going to divide by a 36. We're going to have a k squared is greater than 4, because when we divided, we flipped, which is going to mean the absolute value of k has to be greater than 2. Okay, remember, if it's less than or greater than, you need to think of it as absolute value. So that means the value of k is either going to be smaller than -2, because -3 would have an absolute value greater than 2, or the k value can be greater than regular 2. If I were to graph this, 0 to -2, it would look like this. Welcome back to chapter 3. Okay? That's what that would look like. So in order to have imaginary roots, the k value has to either be smaller than a -2 or larger than a 2. Okay? This little piece is essential, that you can't confuse equal to's and just say, well, it's either this or that, when you're dealing with less thans and greater thans, when you're dealing with imaginaries or real unequal. So real unequals that are greater than, after you've flipped, if you had to, it's absolute value. Okay, you only flip if you're dividing by a negative, guys, or multiplying by a negative. Imaginary started out as less than, but as we arranged everything and divided, we had to flip. If you don't have to flip, obviously it doesn't matter. But still, the absolute value holds true. It has to be answered as an absolute value. Okay? Today you are actually going up to number 32. And there are 2 of those scenarios like what I just taught you.